In this video, I want to take a look at this code I've made where it simulates a bunch of particles, for example 20,000, on the GPU, and so it's updating all the data solely on the GPU, and it's also rendering using the GPU, of course. So it's like fully everything, all the interesting computations are running on the GPU. So let's see how it works. That should not be there. Just gonna remove that. That was just some testing code. Okay, so here we are. And if I run the simulation, you can see that it's evolving these 20,000 particles that all start very close, but because this thing that is simulating is a chaotic system, which we'll get into in a little bit, they tend to spread out, and you can also rotate in 3 dimensions and see where they end up. So that's basically what we're gonna look at today, and we'll add some more features to this program. So the thing I'm actually simulating is this so-called Lorentz system. And you can see kind of the shape that we got is very similar to this one, and these are actually the parameters I used. And the differential equation for this system is quite simple. And if we take a look at the actual compute shader that is updating the positions of the particles, you can see here how it works. So first we calculate dx, dy, and dz. Basically from these equations I just like multiply dt over, don't tell the mathematicians, and then you calculate these quantities on the right hand side, and then you update all the positions by just adding that dx, dy, and dz. That'll give you a new position. So okay, so what do we need to make this work? Actually, we don't need a velocity buffer. That was just some other tests I made, but we need the positions. They need to be sent from the CPU to the GPU. We also need the number of particles. That's just a kind of a sanity check, so we don't try to access something that we shouldn't access. And then we need how much time has passed. So let's take a look at how it works. So here in the main function, let's actually close that. The first thing I do is initialize the particles. And that function is up here, and the particles are put kind of in a line. It's not really important, it's just most interesting if they're a little bit spread out. So we loop over some number of particles, which I defined up here as 20,000. And then we put them in a tetrahedron, which is kind of like a pyramid with a triangular base. So here's kind of a reference drawing of one of the sides, the base of the tetrahedron, and the final vertex is like here, but above everything. So I just set those things up. It's not too interesting. Still the velocities which is kind of left over from something else. Okay, so that initializes some data. And that data is inside this positions array, which is here on the CPU side. Okay, then there is some Raylib stuff. Here I check the maximum group size, which is like how many threads basically can you run on the GPU at once. It's not so important, we don't use it for anything. It's just for reference, you might want to check that. Then we initialize the compute shader, and here a lot of stuff is happening. So first we load the code for the compute shader and we compile it. We compile it here. And then we construct this compute shader program, and then we get rid of the loaded code and basically free that memory. So that is just taking the code in and compiling it. Here is where the transfer of data from the CPU to the GPU happens. And the way you do that in Raylib, and it's very similar interface in like pure OpenGL. You basically create a buffer object, shader storage buffer object, I think it's called, and that will return you an integer, which is kind of like the ID of the buffer. You have to tell it how big it is in bytes. You have to tell it where to get the data from, and then you have to tell it like which mode it's in. Not really copying a lot, so this could arguably be static copy, but it's not too bad. This is the same. And then initially when I made this, there was some problems where it had assumed that the things being loaded was vectors of 4 floats, but I had only uploaded vectors of 3 floats, and that caused some issues. So there's just a sanity check here that everything is as we expect. So it's quite easy to initialize some data on the GPU. In Raylib, you just do this basically. All right, so we have the compute shader. Now we also need a rendering shader, and I don't want to use like a default shader or anything like that. You could probably hook up to Raylib's shader system a little bit better than what I've done. But I made my own rendering shader so that I could, at a more like closer to an OpenGL level, see how to use the same data in the compute shader that updates the particles, and also use that same data without transferring back to the CPU, use that same data to render. So let's see how that is. We again load and compile the shaders, and then we create a program with those shaders. Then you need this vertex array object, which is kind of like stores all the information about all the data for the shader, something like that. We have to make a vertex array, otherwise it doesn't work. So I create, here I'm using actually OpenGL functions directly. So first we generate the vertex array, then we bind it, which is like OpenGL way of saying use this exactly. So we bind the vertex array, then we take this buffer, which importantly is the same buffer that we used up here in the compute shader. There it is. This one. It's the same one. So that means the data is accessible also in the rendering shader. And then you have to set up, it's an attribute, which means that for each vertex, for each vector 4 in this guy, the rendering shader is invoked for each of those. That's why it's an attribute. Anyway, so you do that. That's kind of like normal OpenGL stuff. It's not too interesting. So now we initialize the 2 shaders. Then there is some camera set up. I also removed the cursor. There's some screenshot support if you want to make a GIF or something like that. Then I use Raylib's update camera, so you can actually you can move around like this, and it just works without much trouble. Then do the normal thing of clearing the background, and then here is the interesting. I run the equations of motion on the GPU. If you press R or if you hold down T, this will run. So if we go back here, now I'm kind of like far away because I press G. You cannot see that, but I'm far away. And if I hold down T, they just run. And if I press R, they do a single step. So anyway, you activate the compute shader. that's the first thing you should do before you run it. That is basically you say to OpenGL, use this shader. And for some reason, that's wrong, I suppose. I also set DT here. I don't want to do that, so we remove that. Okay, so I set the number of particles. It's a so-called uniform. So if you remember on the shader, there was these numbers, uniform int, uniform float. That's how you set it from the CPU side. You get the location and then you call set uniform. Then you also have to activate the buffers. So I say that the position buffer should be at location 0. That corresponds to this. And the velocity buffer should be position 1, which corresponds to this. And now if we go back, so that's activated, then we set DT. And let me actually check that it still works, Then I ensure that the DT is not too large, because otherwise this equation of motion become unstable. So anyway, so then we set the DT, then we actually run the compute shader. So here's a run the compute shader, and you can kind of run it in a 3D grid. I just run it in a 1D grid, so just run it for all particles and then 1, 1, because I don't want any additional dimensions, and then we deactivate the compute shader. So when I call this, then this main function is run. And what does it do? First, it gets the index of this thread, this GPU thread, which you can just do global invocation ID .x. It's enough for me to do .x because, as I said here, we just run it on in a one-dimensional dispatch. If the index is higher than the number of particles, it should never happen, but just in case, we return. Because if you get like segmentation faults or anything like that on the GPU, it can be like hard to debug. So here are some parameters for the equations of motion. So if we go back and look here, this is like this is rho. Rho is that one, sigma is that one, beta is that one. And then I update all the facets of the particle. Remember, the particle is kind of like a pyramid, so we have to update multiple points each corner of the pyramid, and that's basically it. So let's go back here. Then we render. So we activate the rendering shader. Also a bit of junk here, but basically use that program. Activate this vertex array object, and then activate the position buffer as the array buffer. Then we set up a perspective projection. I won't really get so much into that, but that's a way of transforming the positions of the particles to wherever they should be relative to the view that you currently have. That's what makes it possible to like move around like this. Then we run it, and then we deactivate it. I have these check error helper functions that just checks if an error happened, because that sometimes happened. And we can go here actually, and we can look at the vertex shader. It's quite simple. It's just the camera matrix times the position. That's a quite normal thing. And the fragment shader just sets a constant color. You could think of doing something more interesting, but for now that's it. Then I call end mode 3D, which is actually a little bit weird, but that is a raylib function that just runs a bunch of like deinitialization things, so I can go back to drawing things normally. If you don't call that, so let's see here, there's some text in the upper left, and if I don't do that, the text just does come up. For some reason I thought, so let's also remove that. Yeah, so there we are. We can run it, we can orbit. All these commands are not so interesting. I will make the source code available so you can just have a look at how it's done there. Okay, so what I want to do in this video, besides that explanation, is to make these things changeable, because these things determine the shape that you get here. So maybe if we can change those values dynamically or whatever, it could be quite interesting to see what you get. So I want to make some sliders basically. That also reminds me we should probably not disable cursor. It's gonna be weird. It's gonna be quite weird. So maybe we do want our own update camera function. But let's not do that right now. So we want some sliders down here that we can pull to change the values of these parameters that go into the equation motion. So the first thing we should do is to define rectangles for rendering and for UI. So here is the full window. That's always 0, 0, and the width and the height. Then we should make, let's call it a rendering rectangle, and that should be like a center rectangle. So I also have this file here that we can include. So define this and include rect.h. Right, so wait, I shouldn't have closed it because I need to look at something. So we have this rectangle center. So we can put this here. And the source rectangle is the width, and we probably want like 80 and 80. So let's see if we can get that working first. Here where we activate it, we should probably take that rendering rectangle and then we need to redefine this function, and I like to call this location. So how does this work? Well, we need to set something called the viewport, like this. And probably we can do it here. So let's see if that worked. And it did indeed work, but you can see the text also changed. So now if we draw everything, you can see it doesn't go fully to the edge. So actually what I want to do beyond that is, let's keep this as the background, but we'll draw the rectangle. In the rendering rectangle, it will be this, and we'll clear the color to maybe 51, 51, 51, so we can actually see the difference. That didn't really work, right? That didn't really work. Yeah, something is weird. So the rectangle is somehow drawn on top of What if I don't draw that? Then we see them. Okay, so actually we have to say end. Maybe we can say end mode 2D. It's a bit weird. It's probably not very logical way to do it, but okay. So basically these end mode something in Raylib, they like dispatch some drawing calls. Okay. So now why is this thing? Well, it should just be that, so what is the matter? Okay, so actually after we've run all this, we should reset the viewport. And then this, okay, so that makes a lot of sense, I think. Okay, so here we go. Now everything is working as I expect. Great. So let's now make some rectangles for the controls. So let's say rectangle sliders rect, and it'll be a rect at the bottom. I do think we have that. We just have bottom, yes. And actually, let me do it like this. So it's the bottom of the window, and we get height of 20%. Draw control sliders. So to begin with, let's just draw something like this. Great. Well, it's not great, but it's something. Let's turn these guys to 0, and now we have this thing. So I actually don't want to really draw those, but let's say we need we'll have like a row slider, which is something like that. So we have left, right, and center. So let's make this one the sigma slider. And actually that one can go in the center, have the same width and the full height. And the beta slider can be that. Okay, so let's think about how a slider works. Well, first it needs a location. Then it also needs a value to control. And the way I usually do it is you give it a pointer to something that it controls. And then you can also give it a label. And you can see that Copilot has already suggested something. So actually we should could also give it a color, but anyway. So here we draw a rectangle over the location. We draw the text. Actually this, I don't want to do this. So this is like the background. And let's say Copilot disable for now. So then I want to turn this location into something like this. Like you take up 20% of the height, and that thing we can draw here, and maybe we draw it in white. So let's start with that. So let's draw a slider, and we'll say it's the row slider, and it needs some kind of value. So we'll say dummy value, and it needs a label. So we'll write row. I think that should do it. So here you have it. Here it is. And actually, one more thing it needs is it needs a minimum value and a maximum value. So I think row, we can say, what is it now? It's 28. So I think we can say, you know, from 0 to probably 100. 100 is fine. Then we can say we have like a progress, which is how far along this slider have we gone. So we need the value. We need to see how far it is from the relative value. And then we need to divide that by max value minus minimum value. And that's like the percentage. So let's draw a circle. And how do we draw a circle? Draw a circle. We do it like this. And we'll say center x is like slider rect dot x plus slider rect width divided by 2. Sorry, height. And then we need the progress. So progress times slider rect times width. And the y is actually always just this thing, but with half. I think. No, why is there? No, sorry, this doesn't make any sense. The height is here. Okay, so it's a bit of a brain fart, but here we go. So center x, center y. And what's the radius? The radius should probably not be too large, so we'll say slider rect dot height times this. That's the radius. And the color can just be black for now. So let's see. Okay, the color should not be black because we have black up here. So the color can be red. So now you can see we have this thing, which is annoyingly like way too large. Okay, so we need to divide by 2. Okay, that's a little bit better. It's not very far along, which is interesting. And I probably want this to be like, let's make it gray white. And the background here can be gray maybe. Actually, let's reverse those. It's not so important. Okay, so that's it. So now we have to say, okay, if now we want to be able to move it. Right, so let's say that we have the position of the mouse. Get mouse position. And then we can check, there's some like check collision stuff in here. Check collision circles. Check collision point circle, that's the one we want. So if if this stuff, then we want to do something. So what's the point? That is the mouse position. What's the center? Suppose we can do it like this. Center X, center Y. And the radius is just the radius. So if they collide, what do we want to do? What do we want to do? And actually, before we get too far with that, I want to also say, draw the label. So the label rect is a rect on the bottom part of the location, and it should have the full width, I guess, and then let's give it 60%, and let's say draw rectangle rect. Let's draw it as blue just to see where it is. And that did not work because this one only takes the height. Okay, that's fine. So it's a bit too high. Yeah, that's it. All right. Now inside that rectangle, we actually want to draw the text. So let's just say draw text. It's the label. And now I have to remind myself what the signature of that function is. Okay, so first we have the label. Then we have the position, which is the label rect, plus maybe a bit of margin. Then that is also the Y, but it's plus the height divided by 2. The font size is 20, it's usually okay, and the text can be black. So now we have this thing here. It's not amazing, but it works. So now if we are colliding with this, and if is mouse button pressed or something like that, is mouse button down, yeah, so is mouse button down, and I think it's mouse left button. And actually, something else we want to do. We want to do this, and we want to collide with a rectangle instead. And the rectangle we want to collide with is the slider rect itself. That will make sense in a little bit. So if the mouse button is down, we have to find like the mouse progress, which is going to be mouse position X minus slider rect.x divided by slider rect width. And then we simply set the value to mouse progress times max value minus minimum value plus minimum value. Okay, so that's fantastic. Now up here in the simulation parameters, we now need these new things like rho and sigma beta. And now we can actually connect this to something. So let's see how that works. One more thing though. Let's also draw the value. So it's going to be something like this. We'll draw 4 label and the actual value, and then let's try to do that. So okay, so rho of course starts out as 0. It's initialized to 0. So we'll do this. And we will check what the other ones were. So this one is 10. This one is 8 divided by 3, which is like 266. Okay, so now we can see here. And now I can also drag it and I can change the value. Cannot get it, it's not so easy to get it all the way to 0, but probably that's fine. And now I can also just click anywhere within here because I'm checking collisions with the slider rectangle, not with the ball itself. Otherwise I have to click the ball all the time. That's would be very annoying. Now I also have these guys, so we can also hook those up. Sigma slider, beta slider, and here's sigma, beta, and sigma. Can also be 1 to 100, but this one probably doesn't need to go that far. Maybe it only goes to 20. So now we have some nice sliders here, but they don't affect the running of the program in any way. And actually, just because it's quite easy, I want to change this one, make it a little bit smaller, maybe even more, maybe even more, maybe even more. That's not, it should be like that. Yeah, okay, that's what I was worried about. It's overlapping slightly. I think we only have 10 to go with here, which is a bit small. What if we make this one 7.5 instead? Yeah, that's a little bit better. And up here, maybe this one doesn't have to be in the center, it can be in the top. But I do think I have something. So no, it's not rect above, it is rect top left. I don't have a top actually, and I really don't. Okay, so for now this is just gonna be, well, you know what, we can do something easily. We can say, let's move the Y back to this, but also add just like tiny bit of margin. So we moved everything up a little bit. And down here where we draw this, maybe we don't want to use bottom, maybe we want to use below similar. So below similar, and shouldn't be location, it should be slider rect. But then probably we want to say, well, actually, let's see how that looks. And then we can even increase the margin just also slightly. So I think that's slightly better. Okay. We have these guys, we can run the simulation, but they don't affect it. So what we need to do is one more thing actually. I think this is a good idea. So let's get the mouse position. And it's a bit weird, but okay. If check collision point rect, if the mouse position is inside the rendering window, then we do this. It's a bit weird because, yeah, the mouse kind of works like it should. Do we also want to say, yeah, anyway, the mouse works like you would expect, but also if you have the so I can move around now, right? If I pull the mouse out. I cannot move with the keys either, but I think that's fine for now. We're just trying to get it to work. All right. So now we can change the values. Now we should hook them up to the compute shader. Now before we can do that, we need to make them uniforms. And do that like this. And there we go. Now they're uniforms. And then when we activate the compute shader, we should also set the other ones. So row location is, actually let's do all of this. So it should be row. And that one we don't need. And what's the value? Okay, it's whatever is in row. And then we do the same a couple of times. And of course this one should be called row, row, row your boat. And here we can just substitute row for sigma. And here we can substitute row for beta. So I think that's actually sufficient. Let's try to run it, and that didn't work. There's some kind of error. So now you can see how the error reporting works. So after activating rendering, there is some kind of invalid operation. And that's because these are not ints, they are actually floats. So, I mean, that's probably why, but now it runs like before. Let's try to update this. It does go somewhat crazy. What if we really throw it up? Okay, it's impossible to see what's happening now. Let's throw it back to 28. And it should kind of collapse back, but it doesn't. Okay. So there it really exploded. Let's try to double this one. Now it doesn't have this spreading out, or at least not as fast. But here it is happening. We can also go in an orbit. So it seems like this sigma is kind of like controlling the size of the holes. If we make it smaller, they should. If we make it really small. What about beta? Let's change that. It's kind of changing the shape. Now they are separated. Okay, so that kind of like these two wings of the shape, how mixed they get somehow. So you can play around with this for a long time. There is some kind of bug, I'm pretty sure, because they shouldn't look like this. I mean, it looks cool, but it looks like the triangles are like really stretched for some bizarre reason. Okay, I think that's it for this video. Hope you liked it, and I will see you in the next one.